Good morning class and welcome to another lecture in sustainable energy technology. Till previous class we have been discussing the physics of a semiconductor, insulator and conductor and what is it that differentiates their different electrical conductivity. We also discussed the idea of a filling fraction and how we can estimate the number or the fraction of electrons that are likely to be found in the conduction band, which is primarily responsible for the transport of electric charge in a solid. And we saw that for semiconductors particularly, the filling fraction increases exponentially with temperature so that pure semiconductors are able to transfer more electricity the higher its temperature. Now, today we will discuss the concept of doping, which is very important in order to generate the PN junction diode. So today we discuss doping of a semiconductor. So here doping is the deliberate addition of impurity atoms into a pure semiconductor material in order to improve its conductivity and other electrical properties. So doping is you are adding a specific impurity atom into your pure semiconductor material in order to improve its conductivity and other electrical properties. So we have two terms. One term is called extrinsic semiconductors. These are doped semiconductors. And intrinsic semiconductors, which are pure semiconductors. Okay. Now the amount of impurity added is usually quite small. So we have several levels of doping. We call light doping to be the case that one impurity atom per 100 million pure semiconductor atom. Okay, and heavy doping involves around one impurity atom per 1000 pure semiconductor atom. Okay. So this one is parts per billion level and this is parts per 1000 level. Okay. So light doping and heavy doping, and you can have multiple ranges between these two as well. Okay. For silicon, the best doping percentage is about 1 impurity atom per 10 to the power 4 to 10 to the power 5 pure atoms. So this translates to 10 to the power 17 to 10 to the power 18 dopant atoms per cc of silicon material. Okay. So for silicon, the base doping percentage is 10 to the power 4 to 1 atom per 10 to the power 4 to 10 to the power 5 pure atoms, which usually translates to 10 to the power 17 to 10 to the power 18 impurity dopant atoms per cc of the silicon material. Now, doping itself is used to improve the electrical properties, conductivity properties of silicon on other semiconductors. Now, why and how does this work? To understand that, we will see that there are two types of doping. One is called N-type doping versus P-type doping. Okay, so there are two types of dopings, N-type and P-type doping. Now, silicon has 4 electrons on its outer valence shell. Okay, so silicon has 4 electrons on its outer valence shell. So suppose you use phosphorus as an impurity. So dopant is phosphorus. This has 5 electrons on its outer valence shell. Hence, when phosphorus is added in silicon, there is an extra electron that cannot be bonded with other silicon atoms. Hence, phosphorus donates one extra free electron to the conduction band. Hence, it is an N-type dopant. Okay. So basically what is happening, silicon has 4 outer electrons on its valence shell, while phosphorus has 5. So when phosphorus is added as an impurity atom within the silicon structure, then there is one extra electron with phosphorus that cannot find a pair within the neighboring silicon atoms. And this extra electron kind of becomes a free electron that is donated onto the valence, the conduction band of the silicon atom structure. And therefore, these are called N-type dopants because they act as electron donors, as they are a source of extra free electrons. But suppose instead of phosphorus we use boron. So boron has 3 electrons on its valence shell. Hence, adding boron to silicon opens up vacancies or holes in the silicon valence band, which can conduct electricity. Hence, these are called p-type semiconductors, as they act as a source of extra holes in silicon valence band. Okay. So boron has 3 electrons on its outer valence shell. So if you add boron within the silicon structure, there will be one open space which cannot be filled by an electron around boron. So an extra hole is added into the valence band of your silicon material when boron is added to it. And this extra hole is also like a free vacancy which can move from one atom to the other, because it's not being one atom to other, and hence can transport charges. So these are hence called p-type semiconductors, because they act as a source of extra vacancies in your silicon structure. So the idea is then like this. This is your pure silicon. This is your valence band. This is your conduction band. Okay. Now this is pure. Now we look at N-type. So suppose phosphorus has been added to it. Then close to the conduction band, the addition of phosphorus creates an extra zone of electrons, of free electrons coming from the phosphorus impurity very close to the conduction band. Extra electron level. Okay. And these are very close to your conduction band, and hence these electrons can easily be promoted to your conduction band and hence help in conducting electricity coming from dopant. Okay. Whereas for a p-type case, you have a set of empty spaces opening up close to the valence band. So these are extra vacancies from p-type dopant. So these holes here can easily move down and create, and these holes can move here. Okay. As electrons can move from here to create this empty space here and fill up this empty space here. So it's as if the vacancies are moving down into your valence band. And this is called a p-type semiconductor. Now the effect of N-type and p-type doping is to raise or lower the Fermi level closer to the conduction and the valence band. So what it looks like, if you look at for the N-type case, if you plot E minus EF by KBT. Okay. Then suppose this is your conduction band and this is your valence band. Originally, the Fermi level was here. Okay. This was your EF for the pure semiconductor. Okay. Now what happens? Because of the presence of the N-type dopant, your Fermi level actually moves upwards towards the conduction band. So this is EF N-type. Okay. So then what happens is that your Fermi level has moved upwards, and hence as a result you are getting far more electrons in the conduction band, whereas there hasn't been any change in the number of electrons in the valence band, because remember that the number of electrons in the valence band is the same because you have as many electrons coming from silicon. The extra electrons in your conduction band is coming from the phosphorus atom. Okay, so this has an effect of raising the Fermi level closer to your conduction band due to the presence of this N-type semiconductor dopant. Now, the exact opposite is the case for holes. So, holes are empty spaces. So, we can evaluate the probability of a hole by plotting, instead of F, 1 minus F, the empty fraction. If F is the filling fraction, 1 minus F is the vacancy fraction. Okay. So we can do the same thing for 1 minus F. So here you have again your conduction band and this is your valence band. Now clearly for 1 minus F, this is the vacancy fraction. So the upper levels of your conduction band are fully vacant, so the probability is 1, and the lower levels of your valence band are fully filled, so completely non-empty because that is the valence band. So here the 1 minus F plot kind of looks like this. Okay, so this is the 1 minus F plot for the pure semiconductor case. Okay, for a p-type case. Now you are doing a p-type doping of this semiconductor. Then your Fermi level for a p-type dopant kind of goes down. So EF p-type. Since your Fermi level has gone down, so this is the undoped and this is the doped. So you are seeing that there is a larger number of vacancies in the doped case for a p-type semiconductor compared to the undoped case, and all these vacancies are being contributed by this set of allowable vacancies that has come up because of the presence of your p-type dopant. So this can be more easily seen in a few associated figures that I will just briefly note from the PPT. So this is basically your silicon semiconductor and its crystal structure. Okay, so there are 4 atoms on its outer shell, and so that creates 4 covalent bonds with other silicon atoms, creating this type of structure. Similar structures also exist, for example, in gallium arsenide compound and cadmium telluride compound, which are also semiconductors. As we discussed, for an isolated atom, all your energy levels are separate into distinct lines that are separated from each other. Now, if you have 3 atoms together, one line breaks down into 3 closely spaced lines representing the 3 atoms for that energy level, and similarly the other lines. And now if you have a large number of atoms in a solid, all of these closely spaced lines become spread out and extremely dense, semi-continuous band. So these are the energy gaps, and these in between are the band gaps. And as we discussed, this is the band gap WG. For semiconductors it's smaller, for insulators it's larger, and for metals and conductors the band gap does not exist. Okay. And as temperature is rising for a semiconductor, what happens is there is enough thermal energy for some of the electrons getting promoted to the upper levels, and this is responsible for the flow of electricity, the movement of holes in the valence band and movement of electrons in the conduction band.